The next section in the chapter we're going to actually skip other than mentioning, hey, it's there. Basically that section says, you know what, sometimes cleavage can tell you about the strain, but not always. Now, foliations and folding. Cleavage fans are the alignment of the cleavage fractures along a fold. They can be convergent or divergent based on the rock type. This tells you about the fold, as well as, of course, what the rock is. Now, competent beds and incompetent beds. This doesn't mean that, some rocks are really good at being rocks and some of them suck at it. What we mean is by competent and incompetent is how sturdy they are, how strong and rigid and versus how mushy and bendable they are. Incompetent rocks like shale and marl are much more plastic and deform more easily. Competent beds like sandstone and limestone are stronger and more rigid and more resistant to bending and folding. Now, with enough heat and pressure, every type of rock will bend and fold. But, based on its competency, the fractures, the cleavage that occurs, will orient differently. Now, if we have a fold, in this case it's an antiform because the hinge is at the top. We don't know young or old, so it's just an antiform, not an anticline. And in this case it's alternating shale and sandstone, designated by SH and SS. You can see here the sandstone, which is a competent rock, has convergent cleavage fans. At the bottom of the fold surface, where's my mouse? So in this top sandstone layer, this bottom edge of the arc, bottom inside edge of the fold, is where the cleavage is converging. In the shale, on the other hand, on the inside of the fold, it's diverging. In this case, it almost looks parallel. Sometimes the divergence will be more obvious, but they're not converging. So it's a divergent cleavage fan because it's an incompetent rock bed. This is also sometimes called axial planar cleavage fans or divergent. And we collectively call this cleavage refraction. It tells us, which way the cleavage is orienting, and you can see clearly as you change from one rock type to another, the angles of the cleavage change. As you get away from the hinge of the fold, it's more and more obvious. Right along the hinge, the cracks are almost all parallel. As you get away from the hinge, there's a very distinct difference between them. Now, the next section looks at lineations. So these are linear features. It could be minerals or it could be some other thing that is in the rock. When we have extreme folding, we get linear features along the edges. The hinges, if they're really sharp, create a linear feature. These are crenulation lineations. Kind of fun to say, crenulation lineation. These are the hinge lines of microfolds. So small tight folds create little lines. Mullions. This is not a haircut. That'd be a mullet. So this is a mullion. Mullions are the cusp-like corrugations at the contact between units. So if the surface between the shale and the sandstone isn't a flat line, it's kind of wavy, these little ridges are called mullions. They're linear features at the contact between rock types. This can happen especially with shale being underneath sandstone, because the shale is an incompetent material, easily deformed, and so as that sandstone builds up and weighs on it, it indents and makes it an uneven surface, and you get these mullions. Oops. Boudins. These are tablet-shaped lenses of a rigid material. So you can see here this little pinched with these necks here, leaves this tablet-shaped flat lens of this rock. Sometimes it's near other parts of the layer, sometimes it's more isolated, but it's a tablet-shaped lens. It's called a boudin. This type of feature in general, not really pertinent to this particular chapter since we're talking about lineations right now, but this is called a pinch swell structure. Sorry. And pinch swell structure is also not very Google safe. Now, surface lineations. If we can have cleavage planes, it's a planar feature, and we have the surface of a fold. So we have two planes intersecting. Where they intersect, we get a linear feature. So we see a line along the surface of this antiform. We can also get lineations when we have a fault. If we have a fault block drop or thrust upwards, we can get linear features. These lines can show us visually the sense of motion. In this case, the block moved straight down. If the block had moved sideways and down at the same time, we would have seen the lines at some angle, giving us, again, the sense of total motion. If it had been a scissor fault, there would be some curvature to them, showing us the scissor motion. So this is, if they're clearly visible, a really easy way to determine the basic sense of motion on a fault block. Sometimes lineations are down at the mineral scale. They're not cracks, they're not folds, they're not striations. They're actual linear minerals all lined up in a linear fashion. You can see here these black and white stripes are minerals all lined up, and on the end of it here you can see more of a polka dot pattern. This lets us know that, hey, these are linear crystals all bundled together. It's not a bunch of planar sheets. Now, this is all well and good, but what good is it? Okay, we looked at a bunch of foliation and a bunch of lineations, and we named them and came up with terminology and descriptions, and why? Well, when we're interpreting a situation, sometimes lineations and foliations can tell us about the things that we can't see. If we don't know where the hinge of a fold is, sometimes the intersection of the bedding cleavage and the surface can tell us somewhat about the fold, especially if we've got two layers and say it's a sandstone and a shale, kind of like we saw in that little drawing. If we see what orientation the cleavage is relative to the beds, that'll tell us, oh, hey, the fold is up here and it's in this direction, so we're on, the limb of an antiform, or we're on the limb of a synform, and you can tell about it by just looking at the bed orientation and the cleavage orientations. Also, you can find out about the strain orientation. Strain tells us about stress fields. Stress fields are incredibly important if you're doing drilling or mining. You want to know what the stress field is in your area. So if we have lineations, they can be parallel to the principal strain, or they can be parallel to a shear direction. So you want to be careful how you're interpreting it, but especially if you have more than one thing to go off of, you can start to figure out strain and stress in your area just by looking at lineations and foliations and cracks to figure out what the folds are and figure out the larger scale things going on. So that finishes up chapter 11, and then this week, of course, we have 2 short chapters, so chapter 12 will be coming along shortly.